Howdy, I'm Smilo and I'm with Moore County Public Library Productions, and we're going to be bringing you many different things here in the next upcoming episodes. Stay tuned.
My name is Alex. I work at NISSAN Protectors. We make engines for Nissans in North America and some that are not North America too. This is one of our robots that we use similar ones for production. We're going to talk a little bit today about history of robots and where they started and some of the limitations and where they're at now, and talk a little bit about robotics in space. So, the very first industrial robot was in General Motors plant in 1961, and its job was to take hot cast parts as they came down the conveyor and put them in a rack to cool down so that some person could then perform the next operation on it. They really needed a robot to do that because it was a hot job and dangerous chemicals and just not someplace you wouldn't want to be to hang out, you know? So that really is what robots still do today, is jobs that are either too repetitive for a person to do, or something that's a dangerous job, or something that is very monotonous, something you have to do over and over and over and over again. You need a robot to do that. It's not going to wear out your hands and arms and all that. One of the benefits of a robot is that it can do that same job over and over again, and can do it very precisely and accurately. And it doesn't need to go home at the end of the day and go to bed, or it doesn't need to stop and eat lunch. You know, it just do the same thing day in day out. So a robot is referred to as an arm. Okay. If you look at the construction of it, it looks very much like your arm. This is the wrist here and your elbow and like your shoulder right here. Enough that this is even referred to as the wrist and the shoulder joint. Okay. And it can do all the same motions that your arm can do. Okay. Twisting around and moving, it can go through everything your arm can do. This obviously has a little bit longer reach than your arm. Different robots for different purposes, or different lengths, different sizes, and how much they can pick up varies also, mostly having to do with the size of the robot. This robot can pick up 14 kilograms, which is about 20 pounds. Okay. But that includes everything that you stick on the end of it. Okay. So the gripper, this thing has a camera that we'll talk about in a minute too. Okay. You can see it can go through all the motions pretty much your hand can do. Okay. There's 6 joints in here that are providing all the motion. Here's one around the base here. There's 2 that rotates right here. 3 rotates right here. 4 goes this way. 5 on the end, and 6. This is on the end right here. Okay. Most industrial robots have either 5 or 6 joints to provide all the motion that they need. So a robot doing something over and over, we talked about that. You could get it to do a monotonous job, something that you wouldn't want to necessarily do all the time. You could do, right? You can do that. really thought about it, you could probably do it faster. You know, that's not an extremely difficult job, but it's going to do that day in, day out. Like I said, it doesn't need to go to bed. Yeah, it doesn't need to take a break, it doesn't need to stretch. Oh, get a hand cramp. So, a limitation to like this right here is the robot really doesn't know what's around it except for what you tell it. Okay? So we can reach in here when it's not looking, and we can steal these out of there. Oh, yeah. Looks pretty stupid now, doesn't it? Well, because we didn't tell it the balls were there. We just told it to do that same motion over and over and over again. So it's going to do what we told it to do. If it was a real application in our plant, then we would probably have like a little laser right here pointing and seeing if there really was a ball, and it would make sure there was one, and it would make sure it picked it up and made sure it set it down, and it would have all that built into the program to make sure that somebody wouldn't have to stand here micromanaging it. They would do what needed to do. Okay. So it'd be nice to give it some kind of awareness of its surroundings. Okay. So one thing you can do is put a camera on the robot to give an idea of what's around it. So we can have it come over and take a picture. We have to train the robot to look for certain shapes and find those shapes and then decide what to do when it sees those shapes. Okay? So we programmed it right now to anywhere there's one of these balls on this plate, anywhere on there, it'll come and pick it up and go dump it on that piece of foam over there. Anywhere that it sees one. Kind of neat, huh? Kind of handy. So it only knows what you program it to do. Okay, so if we stick a different size ball out there, or we stick one of these Jenga cubes out there, right? It doesn't know. See if it does anything with it. No, doesn't have a clue. Because you didn't tell it what to look for. So we can go in and tell it, okay, when you see this, do this. When you see this, do this. And we can program a lot of different things in there to do that. But you have to specifically tell robots, computers, all that stuff. You have to tell it what to do when it encounters something new. Because otherwise, it just doesn't know. It can't just figure it out, right? So, in another program, we told it the shape of the blocks and to do something different when it sees one of the blocks. That's pretty helpful, huh? So you're going to have to do that for each new part you wanted something to do with it, okay? And if there's something not within its visual parameters that you programmed it to look for, like we could stick one of these up on the edge. But because that's a different shape, then it doesn't know what to do with that. Anything that's a different shape. So it takes a picture and we go in and we draw around that picture and we say, okay, when you see this, then here's how you're gonna grip it. It still has to be told specifically each thing. It's not gonna figure anything out. So part of what we need back from the robot too is some kind of action, some kind of something back to us saying how it's doing, okay? So right now it's got a green light saying everything's okay. Well, we come in and we program this, and we'll talk about this in a second. Anytime this robot sees any kind of force on it, it turns on a yellow light saying, hey, I got somebody pushing on me. When it needs some kind of action from us, it turns on this blue light telling us it needs something done. And we can push an emergency stop. It says, okay, I have a fault condition that I can't do anything with. Okay, so that's feedback from the robot. So we know what it's doing. If we're in our plant, then we would normally have like a big touch screen with all the programs running, and it would say specific words telling you what it was doing and if it needed more help, or like if you push that button, then a message would come up saying, hey, this emergency stop button is pushed, so that you could correct that problem. So one of the cool things with this robot is most of the time robots are behind a cage, okay? So most robots don't know that you're there, and if you were to get in their operating space, they would just smash you and not even know that you were there. And most of the time we separate that with the people and the robots with cages, and you have to open up a door which disables the robot and stick a special lock on there that only you have the key to, so that it stays safe the whole time you're in there. Another way we can make it safe is, you see these little yellow little boxes hanging off the corners right here. That is a laser scanner that is sending out laser pulses out in an array, and it sees how long it takes for the laser light to bounce off something, comes back, and it calculates how far away that is. And we programmed it so that anytime that anybody's within about 2 feet of this car, that it's going to see that and slow the robot down. This robot is something called a collaborative robot. That collaborative meaning you can work with it, collaboration, okay? It has special sensors built into this base that can see if any outside force is on the robot, okay? So if it sees it ran into you, then it stops, and if you move out of the way, it'll keep going. It's very, very sensitive enough you can stick your fingers under there and not get them smashed. It'll take off and keep going. If you were to get trapped under the robot, you can also move the robot out of the way. Then because the robot is really just a great big sensor, it also has a feature enabled on it that I can tap it anywhere in here, and it'll tell it to go ahead and finish what you were doing, go back to where you started being pushed at, or you can restart the program. So that's some pretty cool stuff. That has some limitations. Obviously, if you're gonna be around the people, you definitely need to you're going a little bit slower, you need to be more careful than if you're behind a cage. Our robots this size that are in a cage can go 4,000 millimeters a second, so 4 meters a second, like 12 feet. So they're flipping around really fast. This robot can only go at a maximum, if everything's okay, 1,000 millimeters a second. So a lot slower. Okay, still 3 feet a second. That's still pretty fast. But we have to couple that with those laser sensors, or even like some door switches or something that would, when there's people around, it would slow it down and become more sensitive. Okay. Is there any questions? Do you have any questions? I have any questions?
What are some of the other heads that can go on?
Okay. So something that is attached to the end of a robot is called the end effector. Okay. And you have to design your gripper, suction cup, magnet, whatever, to pick up or to move, to do whatever job you're going to do. You have to, that has to be designed and matched to that. As a cool side note, because I don't know where to get that right in there, but so there's a robotic arm on the space station. Okay, it's a cousin to the robotic arm that was on the space shuttle. Okay, and they use it for grabbing satellites and positioning them, or grabbing payload and moving it around, doing what they need to do. Okay. One of the cool things about the new one on the space station is its end effector and its base are the same, and it's not bolted down. Okay. Its gripper can grip, and it passes all the power and everything, and then it can take its base and pick that up and grab onto everything else. And it has multiple stations on the space station, so you don't need one gigantic arm that can reach football fields long. It can actually walk its way down the space station to maneuver to where it needs to be. So there's a cool animation right up here that shows that arm doing that. So it's grabbing a payload out of a satellite. So this is the arm right here, has that extra gripper end effector on the end of it. And you see it's attached to it right there. It's going to set that down. It needs to move it somewhere else, but it can't quite reach. So it sets down its little extra gripper, detaches, moves to a different place, detaches the other arm, picks up its extra cool gripper, and moves that payload the rest of the way to where it needs to be. That's some cool action. So the extra cool gripper on the end of, like this is that's the arm right there, okay? And the extra cool gripper is like 2 of those right on the end of it. It has like 15 axis on the end of it, so we can do a lot of maneuvering, okay? So I think that's about the coolest thing ever. So the robotic arm on the space station a lot of times is operated by the astronauts in space. They have joysticks and multiple joysticks, because instead of 6, it has 7 axes. And they got a bunch of cameras because they can't be right there. So there's cameras on the arm and cameras out here and cameras everywhere so they can see what they're doing. And then one cool thing, you can look up videos of it, they actually have a stripe painted on one arm and not the other arm, so that when it moves over to here, now you got the other end. So all the controls are back. So you gotta know which end you got on the base and which end is out in space. Kind of cool. So they have programs written for it. It has to move very, very slow because everything up there is super, super expensive and can't go to AutoZone and get some new bearings or something for it, right? So, you know, the satellites are millions and millions of dollars and they spend a lot of money getting them up there, so you can't just like snatch that thing and stuff it in here, you know? It takes a serious control. So the arm goes very, very, very slow, super slow. It's better to take a while and not crash than oops, I bumped it, you know? That'd be bad. So, they can operate it from the ground. So that has its own challenges, that there's a big lag time in between the guy on the ground watching it with a camera and up in space, right? That would take some doing. They also have pre-programmed events for the arm that it can do inspections on the outside of the space station and go back and forth, and somebody can just look at the camera feed and not have to be concentrating on moving the arm. We have a program on here, and we hook up a joystick, and you guys can operate the robot and move it around and try to write with the robot. Okay? We're going to do that.
Tammy wanted to know what your robot does at NISSAN.
So this robot has a nice life just traveling around and talking to people.
That's right.
Yeah, it's this robot. It's a test bed so that we can try out different stuff. That's why it's on wheels, so we can roll it to a different part. We can strap something else on it, and we can try out that before we spent the money for another robot and all the other stuff that goes into a project. We can try out the features of it. But this is one of only a handful of collaborative robots that we have. It's because of the speed limitations and force limitations and everything, there's not a whole lot of places that we have the opportunity to use it. There's 2 or 3 of them running right now, as opposed to the probably 200 robots that we have at Deckard. There's over 1,000 robots in Smyrna, and that I know of, they don't have any collaborative robots for yet. It's a new technology. It's all approved and it's good to use, but you can't move any sharp things around with it because it needs to be safe. You know, if this is gonna bump into you, you notice everything's a nice round edge. Well, you can't give it a knife, right? That'd be bad. That wouldn't be safe. So at that point, the whole process needs to be a safe process. So that becomes a challenge when we're dealing with sharp parts. That most of our stuff is like aluminum with a nice machined edge. You know, that's pretty sharp. So we can't do any of that stuff. So and right now they're not. There's bigger collaborative robots, but for a lot of the stuff that we're doing, like moving engine blocks around and stuff like that, there's not the payload that they need for that. So
You had the coolest job ever. That's one share.
That's pretty cool.
Check your jump driver. You should put your other video on today.
So come up and try it out.
So where did you get the joystick from?
I ordered it and
No, I meant like through history. Why did, the joystick even get created?
probably games to start with. I would
Actually,
say.
it was created for the space station and going to the moon. It
Oh,
was directly involved with NASA and going to the moon.
well, that's cool.
That's the only reason why, we have joysticks on our PlayStations and Xboxes, so you can thank, us going to the moon for giving you the ability to play games.
Let's try it out.
I'll try.
You'll try?
I'll try.
I mean, I'm gonna take.
She'll do it.
Adults can try it out too.
Janet can try. Janet wants to. Road trip.
13, so.
He said adults.
Well, I know that, I'm just saying. I'm trying to get the kids to do the
So, yeah, move the joystick in the direction you want it to go, and then when you want to put the pen on the paper, just hold down the red button in the middle. You can sit down with the chair button. You can still see it.
Part of her head was on camera. Part of her head was on camera. It was like,
So see, as you're writing, if you're trying to make a letter, you can see why they have to move everything really, really slow on the space station. Because, that's all it would take is bonk, and yeah, I don't think you want to buy a new satellite.
That is neat.
My bad words.
Definitely take some practice and to get perfect on mine.
You go.
I think we have that. Pretty daggone good.
That's cool. That's super cool.
Yeah, we'll say. No,
Am I up?